We are the beneficiaries of some amazing mathematical processes, sophisticated techniques that have revealed important details about our universe. These processes often involve a formula, like this one. This formula represents hundreds of years of endeavor and many collaborations among great minds. I will show you how to use this powerful mathematical expression and some simple equipment to actually determine the mass of the Earth. Let's start with Isaac Newton. Newton's law of universal gravitation states that two objects in space attract one another with a force that is proportional to the product of their masses, m1 times m2, and inversely proportional to the square of the distance between them, r squared. Looks like this mathematically. Released by Newton in 1686, this amazing insight revolutionized how people thought about the structure of the universe. But it was another 100 years before this brilliant statement was crafted into a precise formula. That feat was accomplished in 1798 when English scientist Henry Cavendish actually measured the force of attraction between two objects. This was an amazing feat. The force of gravitational attraction between small objects is almost impossible to detect. As a result of Cavendish's work, Newton's original statement was refined to this precise formula. F equals G times m1 times m2 divided by r squared. This is similar to Newton's statement, but notice we now have a capital G in the formula and an equal sign. The capital letter G represents the universal gravitational constant. Cavendish's work was essential to determining G. G represents this number, 6.67 times 10 to the minus 11th, and it completes Newton's formula. We can now determine the mass of the Earth. The formula has two masses. The Earth will be one mass, and this sphere, a bocce ball, will be the other. I'll designate this sphere as m1, and the mass of the Earth will be m2. Sitting the bocce ball on our scales, we see that m1 has a mass of 552 grams. That's 0.552 kilograms. Next, we can determine force with a Newton spring scale. The force of gravity acting on the bocce ball is 5.4 newtons. Next, we need the distance from this object to the center of the Earth. That's r in our formula. The ancient Greeks figured this out thousands of years ago. A good estimation for r is 6,371,000 meters. Now we have everything we need to calculate the mass of the Earth. I'm going to rearrange the formula before I plug the numbers in, so our formula becomes this. We are solving for the mass of the Earth, m2. Plugging our numbers in creates this. For clarity, I've left the units out. Just the numbers are displayed. Doing the math, we find that the Earth has a mass of 5.78 times 10 to the 24th kilograms. The NASA website states that the Earth has a mass of 5.97 times 10 to the 24th kilograms. With simple equipment, aided by some powerful math, we have come up with a reasonable approximation for the mass of the Earth. For more science and technology videos and projects, visit our website, ilaroad.com.